Thank you very much. Thank you very much first to the organizers for the kind invitation. And of course, it's great to be in Vienna. And thank you for putting together this wonderful workshop. So I'll be talking about, as the title says, high-frequency spacetimes in general relativity. So I'll explain in a minute what do I mean, what do I want to understand. But the particular problem I'm interested in is a conjecture of Burnett, as you can see already in the outline. So I'll discuss that conjecture. And in fact, sort of there is maybe another conjecture, which is if you turn the original conjecture around, and you can think about that. So that will be the other thing I want to talk about. So let's first describe the setup for which I want to talk about the conjecture. So I'll start with general relativity. So I want to think about, let's say, a Lorentzian metric, so that I don't get into the debate that Andras initiated. I'll not tell you what sign convention I'm going to use. So I just have a Lorentzian metric, so you can think in 3 + 1 dimension, but okay, it can be higher dimensions. So the Einstein's equation is given here. So the Einstein tensor on the left, it's equal to some matter on the right. So of course, one particular interesting case I want to think about would be the vacuum case. Okay. And the question I want to ask is the following. So suppose I have some solutions to the vacuum equation. Okay? But suppose they're high frequency. Okay, so that's what I want to think about. And I'll be precise what high frequency means. So, sorry, I forgot to say. So of course, the Einstein's vacuum equation, you can think of it as a wave equation if you put in suitable coordinates, as Andras told us in the last talk. So now I want to think of a sequence of solutions to the Einstein's vacuum equation, so they don't all satisfy the second one, okay, no matter. And I want them to be high frequency, okay? So let's, for the moment, just take this to be a definition of high frequency, as often is used in the physics literature, starting from the work of Isaacson. So I just want to say, okay, I have something that oscillates more and more, so I have a sequence of numbers, lambda n, which goes to 0, okay? So my metric, I have a sequence which converges. So the lambda captures the conversion rate. So Gn goes to some limit in L infinity. It converges like lambda n. Okay, so it converges. But it has the property that every derivative I take loses me a power of lambda n. Okay? So G converges to the limit like lambda n. The derivative is merely bounded, but the second derivative grows. It's lambda n to the -1. So you can think I have something that's converging, but I have a frequency that's 1 over the amplitude. Okay? So that's let's say it's the high frequency setup from Isaacson. So now the question I want to ask is the following. So of course, well, I know that the Gn converges to the limit uniformly, but the first derivative being merely bounded means that I only in general have weak convergence, not strong convergence. So I want to understand, okay, if I want to think about this nonlinear PDE, so I have some nonlinear terms that are nonlinear in the first derivative of G, can I pass to the limit? Okay? So the question is this also 0? Okay? But if it were, then it won't be so interesting, so I wouldn't be talking. So the answer would be that it's not. And if not, then what can we say, would be the question. Can I say, okay, if not, then of course I can still think about the Einstein's equation, because, well, now I just think of Einstein's equation. Any metric satisfies the Einstein's equation as long as you declare this to be T. So you can say, okay, so I have a limit which is not 0. So then I have some T. So can I say what it is? Okay. So you can think the question would be, can I understand sort of the effective method that describes high frequency gravitational wave? So just to give some references, this comes from sort of a question coming from physics. So this type of sort of perturbations was sort of first considered by Isaacson. Already in Isaacson's work, and very soon after Shugerbois' work, it's already realized that the limit might not be 0. Okay, you can have so let's think a bit about what could happen. So since this is a conference on nonlinear waves and general relativity, let's first think a bit about nonlinear waves. Okay? So this is a simpler case where you can try to understand, okay, a similar question. Right? So in nonlinear wave, you can ask this question. So suppose I have, let's say, some nonlinear wave equation. I write it down. And I want to say I have a sequence of solutions for which I have similar thing as before. Right? Lambda n is a sequence of numbers which goes to 0. So phi n, let's even say, converges to 0. Okay, so it goes to 0, like lambda n. The first derivative is merely bounded. Okay, so this thing doesn't have a strong limit. So because, okay, weak limits and product do not commute, then we know that, okay, the limit is not a solution. But of course, well, we also know that in the world of nonlinear wave equations, you can cook up other examples for which things are nicer. So you can think about just, let's say in 2D, a wave equation with null form on the right side. Okay? And there's a phenomenon called compensated compactness, which tells you that suppose you have this. In fact, you need even weaker. But anyway, suppose you have this. Then you pass the limit, even though, right, for each of these terms, the weak limit and product, they don't commute, but okay, for this combination nonlinear term, it's fine, so you can pass the limit, so the limit is also a solution. Okay? You can see it almost explicitly in this setup, because you can write the right-hand side as as this. Right? So this is just an algebraic identity. Now, I just say the following thing. I just say that phi converges strongly, so phi squared converges strongly. But then, okay, this is a linear operator, so this has the correct distribution of limits. And I make a similar argument here. I know that phi satisfies the PDE, so box phi is bounded, so it has a weak limit, but phi is a strong limit. So then the product would have the correct weak limit. Okay, so then in fact you can pass the limit. And there's of course a very general framework where one thinks about this problem. You can phrase in particular this in the language of the difficult lemma proven by Murad and Tatar, which says that, okay, if you have two things, right, if you have two things, two sequences, let's say U and V, they have vector fields, and they only converge weakly in L2. Of course, the product, they don't have to converge to the correct product. But if you have some structure that compensates you, right, so if you can say that the divergence of one of them is better, the curl of the other is better, then the product, in fact, converges weakly to the correct product in distribution. Okay, so this is what happens in the case of nonlinear wave equations. So now you ask, okay, what happens to Einstein? Right? Do I have, am I in sort of, am I in this situation or sorry, this situation or this situation? Of course, I sort of give away the answer, which is you sort of are in this situation, right? Because you have a sequence of solutions to vacuum, the limit does not have to be vacuum. But as I'll show you, the situation is a little bit more subtle than that. Okay, so let me look at an example of Einstein. So I want to look at first something that I can write down explicitly. So of course, you saw some implicit solutions to the Einstein equation in the last talk, but those you can't really compute. So I do something that even I can compute. I think about the plane waves. Okay, so I just think of as an ansatz a sequence of metric or one parameter family of metrics, which takes this form. Okay, so minus 2 du dv, and then I have some functions dy squared, some function dz squared, and the important things are these functions are functions of v alone. Okay, so everything reduces to ODEs. This in particular is if h is 1 and g is 0, this is a particular way to write down the Minkowski metric. So now I want to look at this, and I just compute what is Ricci. So it turns out in the coordinate basis, almost every component is 0 except for one component. Okay? So then it's quite easy if I'm in this form to try to find solutions to the vacuum Einstein's equation. I just prescribe, let's say, g to be anything. So just prescribe anything. And then I just have to set this to be 0. So I just solve an ODE in h. Okay? So then I have a solution to the vacuum equation. So let's do that. So let's prescribe g. I want g to have the form to have a high frequency. So let's, for instance, saying this is what I can construct as high frequency. Okay. So g lambda. So lambda, remember, goes to 0. It's just the small parameter lambda times a smooth function times something highly oscillatory. And as I said, the amplitude and the frequency, they are inversely proportional. Okay? So then I solve h, right? So I can solve this by set some initial value, and okay, solve it on an interval. Okay, I can have a uniform time of existence, etc. So now I want to pass the limit. Okay, so it's not difficult, of course, to pass the limit for g. Right, the limit is just 0, so that's 0. So now I look at h. So h, I would want to understand what the limit of h is. So I pass the limit of this ODE. But it turns out that, well, okay, now for the limiting h, I can compute the Ricci. Again, it's the same formula. But in this formula, I don't have this, right? Because this is actually 0. The limit is 0. And then I see, going back to pass the limit from the ODE, I have a term which comes from g prime squared. But of course, g prime squared has the sine squared has a low frequency projection, which I get this. So this is what gets the limit. So the limit, therefore, is such that the Ricci curvature is something explicit. It's a positive function, which is non-zero, okay, in general, if k is non-zero. Okay. And now, okay, so if it's non-zero, you can describe what it is. So this is exactly what it is. So Ricci, is equal to this, right? So there's only one component which is non-zero, it is non-negative. Moreover, this component, the coefficient here, is a function of a V alone. Okay, so you can think, draw a picture. This picture is so simple it can't really be called a Penrose diagram. But I have some matter, and the matter, let's say I have constant V, so this is V equals constant. These are null hypersurfaces. Okay, and my matter field here are functions of V alone, which is another way of saying that whatever it's here, it's the same here. So I'm just propagating along these null hypersurfaces. So this can be interpreted in particular as a solution to the Einstein null dust system, where the dust propagates in null direction, and the amplitude satisfies this transport equation. Okay. So this is just one example, and in fact, this example was an example in the paper of Burnett, and based on this example, so this is the paper of Burnett, maybe 1989, 88, and based on this example, he suggested the following conjecture. So he said that, well, okay, we have an example where, okay, you have limits. So in particular, the limit is not vacuum, you have matter, and the matter just propagates in null direction. So what he suggests is that, well, this is sort of the general picture, except the general picture is not that, of course, you are not just propagating in one particular null direction, but you have a superposition of all possible null directions. Okay? So any high frequency limit of vacuum solutions must be isometric to a solution after you identify suitable matter field to, let me call it Einstein-massless Vlasov system. So this is a generalization of this case where you instead have one direction, you integrate over all possible directions. Okay? So this is the original conjecture in the paper. So for the limiting tensor field T, for a sequence of metrics satisfying the assumptions, that's the assumptions that, like what I just told you, you would be able to find some matter field, right, which you can think of as being defined on the cotangent bundle. It tells you something sort of defined at every point in every direction, right, where you're propagating, and you integrate over all that, and you just satisfy the transport equation. Okay, so that's the conjecture. And you can think, of course, the null dust example above is just a particular case where, okay, you only have one delta measure here, and then you propagate one direction. Okay, so here, this is again a quote continuing in the paper of Burnett, and what he says that, okay, so you can have a physical interpretation of what this means. What this means is that if the conjecture is true, we see that particles don't interact directly, so these are sort of how high frequency waves propagate, but they only affect each other through the effect of the background. Because it's still coupled, you will see Einstein-Vlasov. And furthermore, one can actually have a PDE, where one has a complete system describing the effect of high frequency waves on the background spacetime, because it satisfies the Einstein-Vlasov system. Okay. So here's the theorem. The theorem is that the conjecture is true. So set D to be bigger than or equal to 3. And if you set the wave coordinate conditions, and remember in wave coordinate conditions, you can think of this as wave equations. Then assume you have sequence of metric. The sequence is vacuum. Suppose you have these bounds, as we have said before, right? So Gn converges to G infinity uniformly. The first derivative is only bounded, but the second derivative can grow in a way that's inverse to the convergence rate. Suppose you also satisfy the wave coordinate condition. Let me just write it down. This is something that's used to guarantee that your equation, after choosing the gauge, you have a wave equation. Then in fact you can find a non-negative Vlasov measure. Right? So the measure that's sort of in the previous slide. The proper way to think about this is in the co-sphere bundle. So I sort of changed my slide during Andra's talk to match his notation. So you should think this, okay, you have at every point on RD plus 1, and then you have a direction. So it's only a direction that matters. Okay, so you look at all vectors in the cotangent bundle, but then you actually just model scaling. Scaling doesn't matter. You just care about the direction. So think of this as where the measure lives. And G, the limit G, together with this measure, is satisfied with Einstein-Vlasov. So I should tell you more precisely what that means. Okay. So this is the formulation of what Einstein-Vlasov means. Okay. So first, this means Ricci curvature. So I have my Einstein's equation. Einstein tells you Ricci equals to the matter. So Ricci is given by matter. Okay. So Ricci curvature, let's say in the weak formulation, multiplied by any functions. This is the same as you look at the Vlasov measure. Okay. So look at which component, and this is the C in the covector directions, and this would be equal. And then the next thing you know is that this is massless field. Massless means you look at the measure mu. It's supported on the set for which this is the zero set of GCC. Okay, so the P equals 0 in the language of last talk, and so this tells you it's a massless field. It's only on the light, it's supported on the light cone. And finally, it's a Vlasov field. It satisfies the transport equation. Okay? So if you look at the Poisson bracket, precisely defined like this, of any function, which is, let's say, one homogeneous in C, and with the Hamiltonian, so look at this Poisson bracket, this is integrating with respect to the Vlasov measure to 0. So this is a weak formulation, because nu is just a measure of the Vlasov equation. Okay? So that's the result. So I'll explain, of course, where this nu comes from, right? In the actual theorem, why is this true, and what is this nu? Okay. So let me first tell you what actually the nu is. So the original conjecture just told you that there would exist some nu, let's say, for which the limit satisfies Einstein-Vlasov. But in fact, in the process of the proof, I can tell you exactly what the nu is. Okay, there's a way to compute what it is. So it turns out to be a microlocal defect measure. So let me define it precisely here. Okay. So it's this formula, but let me slowly try to explain what it is. So first, let's try to think what's the issue that's happening. So I'm trying to understand the limit of the Ricci tensor. Ricci tensor has some terms which is derivative of G times derivative of G. And the issue, of course, is the derivative of G doesn't, derivative of G squared, right? The weak limit and the product are not commute, right? So I want to understand what happens here. So there's this tool that's introduced by Tatar and Durand, which tries to understand the non-strong convergence of, let's say, the square of derivative of H. So what is it? So it's the following thing. So if you give me, let's say, some components, okay, and I look at H, okay. So H is the difference of Gn minus G infinity. So the derivative square is something that does not have a strong convergence. So what the microlocal defect measure is, you try to understand. Okay, you look at derivative of H and derivative of H. Okay, so this product does not have strong limit. Okay? But what one wants to understand is, for instance, where it does not have strong limits. Okay, so for instance, the one way you can try to understand this is try to understand, okay, derivative of H multiplied by derivative of H multiplied by a function B, right? And then try to see when you have a non-zero limit, and okay, the places for which, right, you have a non-zero limit, right, you can capture by sort of support of B, and then you can detect the location for which you have non-convergence. Okay? But here it does a little bit more. It also tries to detect the direction for which you have non-convergence. So what it does is that, okay, you look at derivative of H, you try to first act on it by a Fourier multiplier of order 0. Okay, so now this is still, so let's say, suppose derivative of H is L2, you act on it by Fourier multiplier of order 0 is still L2. Okay, but now because there's something in Fourier, you capture the direction that you are thinking about, and then you multiply by a function B, and then multiply by dH again. So this, even though H converges to 0, this because it's a product, this does not need to converge to 0. But the claim is, after extracting a subsequence, you can always take a limit, and then there exists some measure for which this limit is equal to this. Okay, so this is the microlocal defect measure. So for any components H, you can define this, right? So H alpha beta, H rho sigma, you can define this object. And the Vlasov measure that I tell you, which is the Vlasov measure of the limit, is just this. Okay, so you have the rho beta, H rho beta, let's say, H alpha delta. Okay, then you can define this object. This is mu. Okay, And then you have similarly for this mu, and then you look at this particular linear combination. So secretly, there's a claim that this is non-negative, and this is actually the thing that arises in this cell. So there's a mu for which this is satisfied, and I tell you explicitly this is mu. So that's it. Okay, so maybe before I go ahead to tell you sort of exactly why one would expect this, why this is true, etc., let me first tell you some related work. So the first results are in the direction of Burnett, was some results of Green and Wald. This is more than 10 years ago. So the statement is the following. So again, you look at the setup I had, right? So you have a sequence of a vacuum, you have some high frequency limit, and you want to understand what's the limiting what the limiting matter is. So you can just think about the limiting matter T, right? So T represents the matter. What they prove is that it's always the case. If you look at the limit, you look at T, first it's trace-free with respect to the limiting metric. And second, it satisfies the weak energy condition. So that is to say, if you take any causal vector, so time-like or null vector, and you contract it with T, then this is not negative. So in particular, if the conjecture of Burnett is true, which okay, it is, at least in the wave coordinate condition, then this is true. Okay, so if you check that if you have the stress energy momentum tensor for the massless Vlasov equation, then this is always true. But okay, they show that okay, this is true. Okay. So that's the first result. So then there are some other results where you can say something about the limit in symmetry or some sort of symmetry reducing. So one class of result is if you, let's say if you are in 3+1 dimension, you can put in a 2-dimensional symmetry. So let's say T2 symmetry. So that's been studied by Lott and Flock and Flock. And in this case, part of the reason is because sort of in this low symmetry, the equation becomes 1+1 dimension. You can actually have well-posedness in very low regularity consistent with this type of high frequency things. So you can really try to understand everything that happens. So you have well-posedness, etc. And you can identify what are the possible matter here. And in this case, well, because you have symmetry, you can only have 2 directions to oscillate, right? You can not oscillate in all possible directions. And you would exactly have null dust in the limit with 2 families of dust. So you can generalize this a bit. So symmetry per se is not really what you need, right? What you need is that, okay, you have T2, but let's say you have, if it's completely symmetric, then of course it's very nice along the T2. But it suffices, in fact, to say that you are very regular along T2. And this turns out to be something that you can propagate dynamically. So if you have initial data for which, okay, you have some T2, foliation of T2, and you're regular along the T2, then you have, again, a well-posedness theory for which a solution also is regular along a suitable foliation of by T2. And then you can understand everything about the limit. Okay, so this is what I did with Igor and Yansky. So in particular, in this case, again, you can classify the limit. The limit, again, would be Einstein null dust. Again, you would only have 2 families of dust because there are only 2 directions you can oscillate. So the other sort of works, sort of maybe most relevant to what I present, is some work in T1 symmetry. So in T1 symmetry, some of the gauge issues are easier. That's why sort of we study this first. And but already there, we see some of the difficulties that I'm going to tell you, and I sort of some of the tools that also we use we first used there. So this is first work with Cécile Huneau in T1 symmetry, and then there's a follow-up work of Guerra and Teixeira da Costa, which give a slightly more streamlined proof of our result. Okay. So let me try to explain the proof. Okay, of the result with Cécile Huneau about the Burnett conjecture. So there are a few things I want to explain. So the first thing I want to explain is how this result has to do with the structure of the Einstein's equation. So I will explain a bit about the Einstein's equation. The second thing I want to explain is where does my colloquial defect measure come in? So why it comes in? And finally, I want to explain sort of how the interplay works, how somehow the limit sort of related to the macrolocal defect measure sees the structure of the equation so that the result is true. So let me first write down the equation. So since I'm interested in wave coordinate, let me already set wave coordinate to be 0. the wave condition here. So h to be what I call h to be 0. So then you can write down what Ricci equals 0 is. Ricci equals 0 is really just a nonlinear wave equation. Okay, so this is the equation. Okay. So now, of course, it's important to analyze the structure of the nonlinearity. Fortunately, sort of this has been analyzed. So one thing you can say is the following. Okay. So you can look at the difference because that's what is the important thing, right? I want to understand the difference to the limit, and it's the difference that goes to 0. And I want to understand the Ricci curvature of the limit, right? Of course, in terms of the original Ricci curvature, which is 0, and things which has to do with the difference. So then you have a bunch of terms. Then you can analyze this. Then, of course, you have box of the difference, right, which is a linear term. And then you have some nonlinear terms. So I identify a particular nonlinear term here, which following the notation of Lindblad-Radliansky is called P, and this is the one of the nonlinear terms. There are other nonlinear terms. There are nonlinear terms which are sort of better in the sense that they are null forms. Okay? So if you remember from the very beginning when we discussed situational nonlinear wave equations, when you have null forms, there's compensated compactness, things are better, right? You can more easily pass the limit. So there are other nonlinear terms, but they are slightly better in the sense, okay, they are total divergence. Okay, so then the weak limit is okay, you can screw up parts away. There are also linear terms, which has an explicit form, which I'm not writing here, and there are terms which are smaller. They are, let's say, cubic and so on. Okay. So the structure it's sort of well understood. Okay. In particular, it's very useful in the work of Lindblad-Radliansky for stability of Minkowski space. So as a result, then, okay, you can almost just say, okay, you know what the limit is, right? Because linear terms, of course, okay, the weak limit is always fine because h goes to 0, so whatever linear term is goes to 0 distribution. Null forms are good, right? Because sort of similar arguments as before for the nonlinear wave case. Total divergence is good, small terms are good. So the only thing is this. So, well, I know already just from this, the limiting Ricci is this. Right? So therefore, I want to understand. I want to understand this. I want to say this has something to do with my nu. But okay, but it's clear that okay, nu is defined so as to has something to do with the quadratic terms in H, right? So I just want to understand. Okay, so if I think of my nu defined sort of with respect to this particular combinations of quadratic of H, I want to understand whether it satisfies the Vlasov equation. I want to understand whether this satisfies some propagation equation. Okay? So one way to think about this is the following. So in the beginning, right, I was giving you an example saying, okay, if you have a general wave equation, if you look at the limit, sort of, then it's bad. Okay. If you have a null form, then it's very good. You have compensated compactness. Here is sort of a mixture in the following sense. So you don't have all null forms. So you don't have compensated compactness. You have a term. Okay, this is not 0. This is a term. But nonetheless, when we analyze this term, as I'll now do, there is another form of compensated compactness, which tells you that, oh, nonetheless, this term actually is it's better than you would naively think. Okay, so let me say more precisely. So what I want to understand now is I have this, right? So this is my I define the t. This is the reason that I define the t with the Merkel-local defect measure because that's the thing that captures, right? So if you remember. That's the thing that sees a derivative of h squared. Okay. So now I want to understand why is it that this satisfies the transport equation. So let's just again recall. Right? So this is the general framework of Merkel-local defect measure, as I said, defined by Girard and Tatar already in the early 90s to measure the location and direction of the failure of strong limit. Right? So the M, the Fourier multiplier, helps you capture the direction, B helps you capture the location. Okay? And you always know that these things exist up to passing to subsequences. Okay, so the first question is sort of where does the transport equation come from? And it turns out the transport equation comes from wave. If you just look at if you just look at high frequency of solutions to wave, so you will see transport equation. Okay? So remember what we wanted to do in our setup is to show that the particular thing that we were looking at, right, the nu satisfies both the statement that it's massless and it's Vlasov, so it's supported on the zero mass shell, and then it satisfies a weak transport equation. It turns out that in the setup of linear equation, this is standard. This is known. Okay. In fact, it's known a long time ago. Okay? So this is not quite the statement as stated by Tatar and Farquhar-Murat because they work in the flat case, but okay, this is exactly what you would prove in this setting with that method. So the statement is simply that if you have linear equation, okay, so let's say if you have box phi n equals 0 and box psi n equals 0, or if you want slightly weaker, you just have a right-hand side, but the right-hand side converges strongly in the L2 node, then in fact you have what you want. Okay? And this turns out to be not so difficult to prove. In fact, you can just prove this by multiplier identities. You can, for instance, look at the definition, right, has this, right? So what you look at is you look at the wave equation, you multiply by, let's say, psi n, you integrate by parts appropriately to get this, and then you will see this drops off. Okay? Similar things can be done if you multiply by derivative of psi and so on, you get this. This just drops off. So this is what I just said. The lemma can be proven by multiplier identities and use the definition of the macro-local defect measure. But the point is you really need somehow to have wave equation. Okay? So this, of course, is a start of trying to say, oh, maybe what we want to say is true, that we have some nonlinear wave equations for h, let's say h, remember it's the difference of g and the limit. Then maybe we can try to apply sort of this type of ideas to try to get that the limit actually satisfies the transport equation. But it's important that the right-hand side here actually converges strongly to 0 in L2. So in fact, you can cook up easily examples where if you just have the right-hand side going to 0 weakly, then this fails. Okay? So it's not true. Okay? So now what happens to our case? In our case, okay, we can take this general framework, try to put in our metric difference, and we look at this. So if it converges strongly in L2 to 0, then we're done. But it turns out that actually it doesn't converge even to 0 weakly. It converges to something else weakly. So, but nonetheless, the claim is that even though the right-hand side does not converge to 0 strongly, if you look at the actual thing that appears, right, which is now a trilinear thing, when you try to look at this equation multiplied by, right, this is already nonlinear. If you just multiply by another copy of h, it's a trilinear thing. You look at that combination of trilinear things added up together. There is cancellation, so that there's still Vlasov equation still holds. So it's a bit like a compensated compactness phenomenon, but now it's at the next level. It's not at the level of saying that the right-hand side will still converge to 0, but it's, okay, the thing that doesn't converge to 0, if you look at the macro-local defect measure, the right-hand side again doesn't converge to 0, but there's cancellation. Okay, there's some cancellation, so that the Vlasov equation is still true. And this is why the conjecture is true. So let me say more precisely. So what do we have to understand? So what we have to understand, so I told you that you try to prove this by multiplier identities, right? So you will look at the wave equation for h, right, which we recall is something that looks like this, right? So I have a wave equation for h, okay, and I multiply by dh, right? And I want to say I can, all the nonlinear terms, they should at the limit be 0 somehow. So what I really have to understand are terms that look like this. Okay? So I really want to understand terms that look like this. Sorry, can I see? Okay, this, where A is a zeroth order pseudo differential operator, right? You should think this is my M and B, right? So Fourier multiply and then multiply by B. So I have my derivative of h, is a trilinear term. H goes to 0, but derivative of h is just bounded. Okay? So if I look at generally a combination like this, of course, again, because products and weak limits don't commute, the limit is not 0. Okay? But nonetheless, I'm not looking at general things like this. I'm looking at the Einstein's equation. So I have some particular term that I have, right? So particularly if you look again at the structure, right? There's something very specific. I have terms which I can think of maybe as good, right? Null form terms. And I have terms which they're maybe not very good, but they're explicit. I can try to compute with them. Let's see what happens. So now let's first try to understand the following. So I have various terms, right? I have, as I said, some null form terms. some terms which are not null forms. So suppose you have null forms, so I wrote down the classical null forms. So the claim is actually those are always fine. So in fact, this in general doesn't go to 0. If you have null form, then actually if you look at a trilinear combination like this always goes to 0. And I want to emphasize this. This is a genuinely trilinear estimate, in the sense that this goes to 0. When proving this, you do need not only that derivative of Hn is bounded, you also need some sort of waveness property of H. You need that wave actually satisfy some sort of wave equation, so that let's say box of X is bounded. Okay? So heuristically, what you want to do is the following. You want to say that so I forgot the word that Ben used yesterday. He introduced a word. What is it? Flip. Okay, I didn't know. Okay, so this is slightly worse than a flip. This is sort of a lie, but okay. But anyways, this is just to think. Okay, so what I want to think is that the null form allows you to sort of reshuffle the derivatives. Okay. So what you want to say is, you have derivative, right? H is derivative. So, but I want to reshuffle so that I would have derivative, again, derivative, but one of the derivatives I can think of as box 2 1/2. Okay. Then again, because box H is better, H satisfies the wave equation, so I can think of like this. And then because box H is bounded, right? Derivative of H is bounded, but H itself converges, so this converges. So the exact implementation, what we actually do is we use the normal form estimates of Alex and Benoit, both here, I think. Just adapt to our case where we have a variable coefficient setting, but a very specific variable coefficient setting in the sense that we know sort of things are of a particular frequency. Right? Remember, the frequency and the amplitude are related. Okay? And we use their estimate, which try to treat exactly this type of trilinear terms in the setup of trying to prove stability Minkowski for the Klein-Gordon field. Okay, so then these are good, right? Null forms are good. So, but remember, we don't always have null forms, right? So that is in particular the reason that somehow the limit is not vacuum. But it turns out there are some more miraculous cancellations that happens when we do the computation. So let me just very quickly say a few words. So one of the things that it's important is the following. So I told you that this nu, right? This nu is whatever happens to be the limiting Ricci, has to do with the limiting Ricci. It satisfies the Vlasov equation. Remember, nu is defined to be linear combination of this mu's, right? So if I look at H alpha beta H sigma delta, right, then I get this mu, this particular, right? This is a linear combination. So it turns out that there are more subtle cancellations, which are more than the null form, which you can't see with the with the mu's. Okay, so for each actually, it's not 0. Right? That's what I must have meant to say. Okay, so for each of this is not 0. Okay, it's not 0, but the particular linear combination is 0. Okay? So first of all, for the linear term, there's nothing you do because this is completely algebraic. So you just compute that there's a linear term, and it turns out that it just cancels in the limit. But for the nonlinear term, it's a bit more dangerous because there are terms that do not satisfy the null condition. And of course, what I used earlier by the Ionescu-Pasaldo estimate, I certainly need the null condition. But it turns out that something like this happens. Okay? So you're not supposed to really read this, but only read the spirit of this. So what does this mean? So I have, right? Remember, I have derivative of H, derivative of H, derivative of H. And I want to say that, well, I can transform one of the bad terms, let's say, by some algebraic manipulation so as to get only null form terms. Okay? So that's what happens. And this involves actually, I have to use the structure of how things are contracted between sort of the term that I'm multiplying and the nonlinear term that arises. And use this up to a better term. You can say that you can make it just null form. Okay? And it turns out that both terms in P satisfy this, and even the quasi-linear term satisfies this. If you throw away some frequency which you can already control, the most dangerous frequency, there's again a structure like this. You can create a null form. So that's the crux of the proof. So how am I doing on time? I have 15, 17. Okay, good. So that's the proof of the Burnett conjecture. So now I want to continue So actually, in the paper of Burnett, he said a little bit more than just the conjecture I just showed you. He suggested something which I would like to call the reverse Burnett conjecture, although he didn't really quite formulate as a conjecture. So let me call it this. So remember what the Burnett conjecture says is the following. So suppose you have limit of a vacuum, then the limit must be a solution of Einstein-Vlasov. Okay? You can ask, well, do you get everything, right? That's a natural question. If you give me something which solves Einstein-Vlasov, can I achieve it as a limit of vacuum? Okay? So there's a sense that Burnett was already saying this, that any solution to the Einstein-Vlasov can be locally achieved as high-frequency limit of vacuum solution. So this is sort of his more precise words. So he said it would be interesting to know if the converse of the above conjecture is true. Okay? So the above conjecture meaning the conjecture that we just discussed. And the converse would be the statement that given a metric on a fixed manifold and a scalar field A on the null cotangent bundle constructed from M such that it satisfies the Vlasov equation, Einstein-Vlasov equation, then there exists a one-parameter family of metrics, right, which satisfy a particular vacuum equation, etc., satisfy the condition what equal 1 to 4, so that the limit is what you have. If this is true, then we do not need to impose any restrictions on A and G. Okay, then here and okay, this is a complete characterization of what's possible. So this is a question of suppose you give me a solution to Einstein-massless Vlasov. Can I construct, let's say, a sequence of high-frequency vacuum solution which achieves this limit? So why is this interesting? Well, okay, it's interesting because okay, well, first you understand high-frequency things, but there's another reason that sort of is interesting because it forces you to try to understand low regularity solutions to Einstein's equation. So this, if you want to understand this conjecture, you have to understand something low frequency. Why is that the case? Because suppose you have a sequence of Einstein vacuum solutions, and suppose you know that your sequence bounded uniformly in some space which is above H1. Okay? Then I claim the limit is uninteresting. Okay? This is because if you have this, then immediately you say that locally you are compact in H1. So the first derivative strong limits. The whole issue that we are studying is sort of the non-convergence of weak limits and products. So then if your strong limits, the limit already has to be vacuum, then there's nothing to study. Okay? So if you have to solve this, you have to understand solution which is below at or below H1. Okay? So of course, this is much lower than the general threshold that we know to solve the Einstein's equation, which is unit H2 of the initial data. And this is already a rather difficult result of Klein-Roniansky-Châtel, proving the so-called bounded electrochemical conjecture. But of course, the point here is, okay, I'm not interested in general local existence result. That would be too difficult. I'm just interested in some very specific thing. You give me some Einstein-massless Vlasov. Am I able to construct something that is very, very low regularity, but very specific, that converges to the limit that I want? The full conjecture, of course, as stated here, is still open. But in the remaining time, I want to tell you some examples for which this is known. Some of the examples are real examples. Some of the examples are imagined examples. You'll see what I mean. Okay, so here's the first class of result that one can prove. So these are very nice results of Arthur Tauti. So here's the following. The following is the statement. So what you want to do is, okay, I first want to understand one simple case of this conjecture, which is, okay, I'm not thinking of general Einstein-massless Vlasov, right? Which is I have these type of things but integrated in many different directions. I only want to, let's say, have a few directions, okay? Let's say 2000. Okay. And moreover, I want some smallness. Okay, I want in a regime where okay everything is close to flat, but I have some sort of 2000 families of things propagating in different directions, and this is the setting for which Tauti solved the problem. So give me sufficiently regular and small and just local in time, let's say, or even just local in space-time. Solution to the Einstein-Dust system where I only have finitely many dust. Right? So this is I have finitely many, so from let's say 1 to 2000. So I have my metric, and I have this are the dust variables. So U will now be the dust direction, right? Like these null hypersurfaces, but I have different finitely many, and each of these has an amplitude, okay, F. I'm given sort of a solution to Einstein now dust. Right? So this is Einstein's equation. The right-hand side is the matter. This is the dust. Okay, I have finitely many. So you could think, for instance, it's the superposition of the Burnett example. Okay? And each of which, the now dust, of course, has to satisfy the equation for now dust, which is to say, first, if you look at U, it has to be now hypersurface. So as to all these hypersurfaces are null. This is encoded here. And moreover, the amplitude has to satisfy the transport equation, and that's encoded here. Okay? So suppose you already have some limiting solution, but only in the case where the Vlasov measure is a finite linear combination of delta measures, okay? And small. Okay. In this case, the theorem says that you can actually do it. You can actually find solutions to the Einstein vacuum equations, for which you can achieve the given thing as a high frequency limit. In particular, it's a C0 limit. So how should one think of this? One should think of this as a geometric optics construction. Okay. So what you want to do is, okay, you want to construct, so G0 is given. You want to construct G lambda, right, which is a source of vacuum equation. And you want to have G lambda, right, so that which is a correction to G with some precisely prescribed high frequency things, right? So this is really like, remember from the plane wave example, right? It's really like this. There's a small parameter lambda that it oscillates at frequency 1 over lambda, and then I have my F. This F is constructed. This F is constructed from this F, but it's not the same thing. And in order to understand this, one needs to understand some of the gauge issues. So this, let me call it F1. Okay. And what you want to say is because again, if you look at the product of the derivative, there's a low frequency projection, so it would look like this, and you can still make this satisfy the vacuum equation without the right. Okay. So this is the thing that you want to close. So notice again, in particular, that because you have a term that looks like this, if let's say U and F are regular, this thing is of course in L2 base top left space is no better than H1. Okay, but this is extremely specific. This error term I can put it somewhere better than H1, so one could close this problem. So this actually, there was some earlier work of this. Actually, already Choquet-Bois has thought about this type of construction in the case n equals 1. And she constructed a formal approximate solution. So it's not exact solution, but okay, it's almost exact solution in the sense that Ricci of G lambda is more in terms of lambda. It's not 0, but it's more. Okay, so that already that type of idea was already there a long time ago. Cécile Huneau and I have done a similar construction like this in T1 symmetry. The key again there is the gauge is easier to understand, and there are very non-trivial things to understand the gauge, which is overcome by tau. Okay, so that's the first class of examples that you can do. Okay, so now let's look at a very different class of examples. So now I don't have smallness. So let me first tell a story. So this is a paper of Singh, which is from 1957. So what's in this paper? This paper, Singh constructed explicit what's called now-dust-shell solution to the Einstein equations. So what does that mean? So let me recycle my picture. So what this means is that he constructed a solution to the Einstein's equation, and in this solution, there's a distinguished null hypersurface which is special. Okay, and the solution is such that you have vacuum here, and you have vacuum here. Okay, in fact, it's a bit better than that. You are Minkowski here, and you are Schwarzschild here. So Schwarzschild here. Okay? But in the junction, there is a distinguished null hypersurface, right? Where you are not vacuum, you actually have. Oh, sorry. I got my time wrong. Oh, that's why when I asked you, do I have? Okay. Okay. I'm sorry. Okay. Okay. Sorry. I thought. Okay, I started. Okay. Okay. Let me just finish this and I skip the remaining examples. You should. Okay. So right, so there's this example where here there's actually a matter field, but the matter field is it's a delta measure. Okay, so there's a delta measure of dust. Okay, so let me just quickly tell you what I want to say. So you want to ask the question whether you can prove a general local existence theory for dust. Okay, and let me just, okay, long story short, let me just tell you the story. So you can ask whether you can prove a very low regularity thing to have null dust, which is the delta measure here. And the theorem with Igor and Yansky is that you can do this. You can have local solutions, possibly even with interaction of two dust. And the point is that this you can prove using the Burnett conjecture, Burnett connection. So the point is we could do this, but we try to ask if you have null dust data, can you solve for a null dust solution? What you could do is that you could try to solve a vacuum problem, which we understood before for spacetimes with regular direction in certain which are regular in certain direction, and we can try to use the fact that okay, if you find a sequence of data which converges to the data that I want, which concentrates at the null hypersurface, I can use the vacuum result to get vacuum solutions. And Burnett tells me that I converge to null dust solution, and this is actually the null dust shell solution that I want, and one can make a construction using this connection. Okay, I'm sorry that I didn't read the time correctly, so let me just finish here. Sorry. All right, thank you very much.